Thanks, everyone. Thanks for switching with me, Lynn. I just drove down from Boulder this morning, and it was a pretty rough drive. I didn't see pavement or lines on the road until Gunnison. And we had about 36 inches in Boulder in the last 8 days. Anyway, that's another story. But what I'm here today to talk to you about is hydrologic characterization of the Nelson Tunnel mine drainage. I'm sure a lot of folks in here are familiar, maybe some are not. I'm Rory Cowie. This work is primarily with myself and my advisor Mark Williams at CU Boulder, Mike Wireman of the US EPA, and Jeff Graves from DRMS. Where do I come in? I guess what I would say quickly is I want to acknowledge that I'm also an employee for Mountain Studies Institute. I've worked for them for almost 10 years now doing different sorts of project management, and it's led me into graduate school, and I'm in the final stages of my PhD work. And this is one of the projects that I've been fortunate enough to come upon only in the last year. So I'm very new. I know there's probably people in this room that talked about this project for decades. And so I am new to it, but I feel very fortunate to be able to do a little bit of work here and learn about the story. So just to put it in context, this guy seems to hang out at the entrance, and I just thought it's kind of funny when you think, as we go through this story today, we're going to think about geologic timescales, human timescales, mining impacts, things like that. And you know, I just was thinking when I was driving up there, I bet these guys were here before the mine went in, and they're still here now. So just kind of the gatekeepers, I guess, of the area puts in perspective that it's not just our area for people. So really important up front, which I think is a big part of this conference, is to talk about what are the partners involved in a project of this scale. Of course, the US EPA Region 8, because this is an NPL site, and also the Colorado Department of Public Health and Environment is involved with this. It's where funding comes direct, specifically for my research. DRMS has been a big part of this, working with Jeff Graves for access into the mines, and also a lot of information and knowledge based on their experiences. The university is where I'm from. The university provides the opportunity to do laboratory analysis and kind of cutting-edge research in connection with these other projects and apply them to a unique setting. I also want to acknowledge Creede Byington. He is a private consultant who's been doing a lot of work and has recently completed a report for the EPA as part of this project, which sheds a lot of light on background and geologic information. He's a geologist by trade. I also want to acknowledge Rio Grande, Silver, Hecla, or if these names change, mining companies. Particularly in this case, as we'll learn as I go through the story, this isn't related to other mining operations adjacent to the Nelson Tunnel site. I also want to acknowledge the Willow Creek Reclamation Committee and Zeke and local groups that have done a lot of work with this area, so they're ongoing, whether it's restoration projects in the greater mining area, and also providing connections for outsiders like myself to come in, who to talk to learn information. And of course the local citizens also have provided us with a ton of background information, folks that were in these mines when they were open. There's information that we can't get to today, whether or not tunnels connect, for example, can be very valuable. So it's a really group effort, it's not just one group. So here we are. This is on the left here is the Nelson portal. This is the question. This is the money spot. This is the water coming out of this mine complex. Directly to the right of it is the Commodore 5 tunnel, and this, in comparison, is about 40 feet above where the Nelson tunnel is elevationally. This picture would be just to your left here. The Nelson tunnel clearly has collapsed at the portal, but they're still discharging. And so that's the target question. Just to kind of put it in perspective, we're talking about zinc and cadmium loads primarily are the metals of concern in terms of AMD. For numbers, you can think of the zinc loads as being anywhere between 163 to 400 pounds a day coming into Willow Creek from this site. It's about 75% of the total load from the whole Willow Creek watershed. And cadmium is second on that list. We could say it's about 50% of load. Load, I guess you need some perspective on flow. The flow rates now are about 250, 350 gallons a minute. This has changed a lot over time. When water first started coming out of the mines, we were talking about 9,000 gallons a minute. In 1902, farmers wanted to put water rights on these 9,000 gallons of water coming out of the mine tunnel downstream. By the 1920s, the discharge coming out of here was reduced to maybe 1,500 gallons a minute. And now it's relatively stabilized in the last 10 years of our records, and it's down around this 300 GPM, just for perspective. So there's basically a dueling conceptual model going on right now of where does this water come from that's coming out of this mine. Yes, it comes from inside the mine. Yes, all water eventually shows up as precipitation someday and then goes through a hydrologic system. But the two kind of questions are, is the water predominantly new from snowmelt and summer precipitation, therefore showing annual cycles and fluctuations that are driven by near closer flow paths, shorter distances, shorter residence times of the water? Or is there a lot of older regional groundwater flow that can be much older in time, longer flow paths from the point of infiltration in the ground to exit at the mine? And an accurate characterization of these topics will impact your remediation options in the long run. So a little outline today, and I'm going to be trying to stay on time here. I'm going to go through a real quick geological characterization of this area. I'm a hydrologist by trade, so if I misspeak on any of the geological components, feel free to chime in, but I'm learning. Mine complex characterization, what's going on in the mine? How can we figure it out? This is an abandoned mine that we have very limited access points to it, so we're using where we can get to it to understand different things going on. And then hydrologic characterization is my focus. I'm going to talk to you about the kind of science behind what are we doing to look at the water to figure out these questions of where is it coming from. And then we'll kind of end with the goal of getting a hydrogeologic conceptual model. So how do we conceptualize this whole system? And from that information, what can we do with it? How does it help remediation options? How does it inform local watershed groups? How does it inform mining companies that may be interested in doing more work in that area? So here, this is from Craig Byington's work. Just to kind of set it up, we all know Creede sits in San Juan Mountains, volcanic activity. What you just see here is these resurgent domes and the forms of calderas. The Creede caldera, for example. Creede basically sits at the north end of that caldera. And what we want to talk about here is the basic geology is when you have caldera formation and this part of the ground surface sinks, it moves up and down, it's going to cause fracturing to the surrounding bedrock geology. Here's a little bit faded out. So here's a Google Earth image, and to kind of put it in perspective, if you think about here, we're looking down at Creede, and here's that Creede caldera, and it's a very classic telltale sign that here's the river. The river wraps right around the edge of that caldera. The mining districts are all right here to the north, and the water eventually starts. This red arrow would be your input. So these are watershed boundary on the upper limit where your precipitation comes in, and eventually it's going to make its way down to the river. And the question is, what's going on in between? So here's to look at a little bit closer. It's not a great picture, but essentially the mining district in Creede, we're going after a couple of major faults. Faults are where mineralization occurs, and the main one is the Amethyst Fault, which is pretty much directly in line with the Nelson Portal. So they went in and the workings go along these faults and then they expand off of these tunnels. Another one that's next to it is the Bulldog Fault, and this is called the Graben structure. And basically these two faults, you have an intergraben area in between them, which has dense extension fractures and faults, which can create different degrees of porosity and permeability. Also, we know of some veins, which are also fractures in the rock that go between these two faults. I thought this was kind of a cool picture. So this is going into the Commodore tunnel, and basically you're on the Commodore level, and we're on the train going into the mine. And if you look at the angle of the wall, you can tell that this is following a fault. So we're sitting upright on the train, and there's not a lot of headspace, so to speak, because everything's a little off kilter. So I'll point out real quickly how do we get after the water. So we want to do some surface sampling. In 2009 and 10, which was work done by another student previous to myself, there was a bunch of sampling done at as many springs and surface locations in this area that we could find, as well as the Nelson Portal, which is of question, and West Willow Creek, which is right adjacent to it. In 2012-13, which is ongoing now, we've added some additional sites. And to put the sites in perspective, here's the Nelson Tunnel, and here is the Amethyst is here, and the Bulldog is here. We've been able to sample the HW4 well, which is was actually put in by Rio Grande Silver as part of their potential exploration back into the Bulldog. So pulling water that's in those mine workings, as well as a domestic well that sits in the intergraben area between the two, and some seeps and springs in other areas to represent groundwater coming out. So vertical view, this is kind of cool. It shows you how you can use a hand-drawn map from early 1900s. And this is the vertical complex, so you can think about this as the mountainside if you sliced it open. And here's all the mine workings and all the different levels. This is the Commodore 5 level that we're going in now. A lot of these other levels and connections are no longer structurally sound. So this is the main way in and out. And this line under here shows you where the Nelson Tunnel is. And the Nelson Tunnel, as I said, is about 40 feet below the Commodore and slightly offset. And basically what I want to point out here is you can see even on this map from then, we see some deep workings where they tried to do some exploration down at deeper levels. And this exploration ended up going away, not continuing, partially because of water infiltration at that point, and also because of lower grade of the ore at that point. And so basically what you can think of is this is the water level now, because the water comes out the Nelson Portal. So looking at the mine system along these shafts, the Nelson is in yellow, Commodore in blue, and basically these are all the different places where there's interconnections between these two levels. And here is sampling sites with some sample numbers from the original sampling. And basically what we want to do is get back into the mine and sample the water as many places as we can where there's water, and where that water eventually, to figure out how it's getting in here and moving out to the portal. So going in and finding how to get a hold of water, the RMS folks can relate to some of this. This is not, it's not currently functioning infrastructure. So you have to do a lot of climbing around and going over big dark holes and hoping the timbers hold together to get between shafts. Kind of interesting to give you a perspective of the work. Here's the Nelson, and here is a flow gauge inside it. So we're measuring the flow of water along the tunnel. You can see this is very, at this point, low quality water in terms of acid mine drainage standpoint. Another perspective in the tunnel, and going back in these tunnels to collect water at different places and figure out the rate of movement. Some sampling. We also found some places where there was upwelling water in certain shafts, and we went in and took PVC pipes and penetrated down to depths as far as we could go and suctioned water out of these places to collect samples for analysis. This is probably my favorite. This is the Berkshire Shaft. So this is about a 30-foot ladder. You climb down the ladder, and then you stand on these floating timbers there's 120 feet of known water depth below you, and you try to penetrate this water with your PVC pipes to get at the water at different depths and pull that water out. So,
what's the temperature of the water?
The temperature of the water here is 14 to 16 degrees Celsius. So it's raised, it's warmer. It's certainly warmer than your surface water or your springs in that area. So how do we do hydrologic characterization? So the work that I'm interested in is looking at stable water isotopes, O18 and deuterium. And basically stable water isotopes can provide you information on the different sources of water coming in because signatures of precipitation change through time. I'm not going to spend a lot of time on the details of this science because I figured that wasn't really the focal point of this talk. So that's why if you have questions on this sort of stuff, we can talk. I just need to bring it in though because that's how we get to the end story. So radioactive water isotopes, tritium is something we measure. Tritium has a half-life of 12 years, so it's something you can use to look at water ages on the order of decades. We also do radiocarbon dating, which is carbon-14 dating of dissolved inorganic and dissolved organic carbon. So that's the dissolved carbon in groundwater. Radiocarbon dating, radiocarbon's half-life is 7,000 years, so you can tell you can tell a lot longer time span with radiocarbon dating. We're also looking at strontium isotopes, which are another dating technique depending on the amount of time water spends underground. It's going to have different geochemical signals. And then, of course, there's metals and solute chemistry, which are really good at providing time series of different waters as you look at them over time and figuring out dilutions versus higher concentrations of pollution at different source points. So real quick, I'll go through some of these results just to show you that we have data. The oxygen isotopes, this is deuterium and O18. Basically, we're just looking at samples along the line. What I want to point out here, this is what rain looks like. This is what snow looks like. This is what our mine waters look like and some of the springs that we've sampled. What you see is they're in between. Any groundwater you pull out should be between rain and snow because that's where it came from. But where it sits on this line gives you an idea of the influence, and how much it's moving along the line can tell you how much the source, rain versus snow, is changing through time. So the important thing here is that more or less they're clustered, there's not a lot of movement. That means that water is well mixed between rain and snow, and it's staying similar. We have one mine sample that doesn't follow that trend, and what happens here is this mine sample most likely is a location where we're receiving fresh, new, recent snowmelt. So snowmelt from that year is going to have a -20 number for oxygen 18. If the mine sample plots like that and the rest of them that are down the tunnel don't, that's a different source of water. So delta 18 values, this is just the range. What I want to point out here is within the Nelson tunnel, let's just look at one number. The mean in this tunnel is roughly -14.9. And what I can show you is the change is not very big at most of these sites. There is an exception. There's a couple of sites, the Del Monte rays and the Corkscrew rays, where the O18 value at different times of the year changes. That's suggesting the water source coming into those sites is changing, fluctuating with the change in the input signal. If we go on to look at the O18 of wells, springs, and surface waters that we've sampled, what you can see here is they're all fairly steady, your springs and wells, and they're a little bit different than the water coming out of the Nelson Tunnel. They're they're -15, slightly more depleted in O18. One thing you can see here, this is West Willow Creek, and this is at two different times of the year. And so this is the creek flowing by the mine. And what you can see is the creek water changes by 5 per mil between June, when it's at West number 2 is June during snowmelt, so the creek looks like snowmelt. The other one's in October, so that's base flow in the stream. So the stream water is changing within the year, whereas water coming out of springs and the water in the Nelson Tunnel does not show that large variation from one season to the next. So what I want to point out here is this is looking at precipitation. So just the same kind of notion. This is the input signal, and this is combining a whole bunch of data that we have from Creede and Durango. Regional weather patterns allow us to combine some of these data from different places, because not all sites have a ton of data. But what you see is there's a big annual swing, and that's well defined by the range in these values of precipitation that go from minus 18 or 20 in the winter to only minus 2 or 3 in the summer. Over here is tritium, and what we're going to talk about next is tritium. So tritium and the precipitation, let's just again not go into it, but look at numbers. The range in tritium is between 3 and 6 right now. So here's tritium precipitation values, same, just a different graphical representation of the same information, where you have a range in tritium values of 3 to 5 in precip. We can see the average is about 5 coming in now. Here is the values of springs and wells. Notice the tritium value of springs and wells is higher than now. Tritium is radioactive, it breaks down. So any water that comes in at a 5 is not going to have a higher signal. The only way it has higher tritium values if it has some older water that has bomb spike water. We produced a whole bunch of tritium in our rain in the 1960s with thermonuclear weapons testing. And so increased levels mean that these springs have some degree of water that's from that older age. Anything before 1950 will have no tritium in it because the half-life's 12 years, it breaks down, goes away. So this is just kind of qualitative. So now look at the tritium in the Nelson Tunnel. What you see is that the majority of the sites are below 1 tritium unit. And so pretty low tritium, so they've decayed. Anything that is below 1, if it's we're going to stay qualitative here, that's presumably pre-1950 water. So it tells us it's older than 1950 because it doesn't have bomb spike water in it, and its levels are near detection, which is about a half a tritium unit. And so what you can see is those same 2 sites that I showed you, the 018 signal was much different. Same thing here, different tritium, higher tritium values. Corkscrew rays, tritium, boom, looks just like precipitation. So it's another checkpoint, another way to look and see if that water looks different. Now to radiocarbon dating. These are preliminary data from a number of places within the mine. This is going from the back of the mine out to the portal, basically Berkshire No Name Bachelor. We're moving from deep in to out. What you see in the first round of sampling was ages in the age of 10,000 to 12,000 years old. These are dissolved inorganic carbon ranges. They need to be age corrected, which we're doing now with dissolved organic carbon ranges. I'll just leave it at that. So these are not absolute ages, but they are giving you a relative value. Now, here's some radiocarbon ages looking in kind of visual perspective that I just collected last fall. So the furthest point back, this is the Berkshire Shaft. So that was that sketchy shaft full of log debris. In that shaft, I went down to different depths. At 65 feet below the surface of the shaft, the percent of modern carbon was about 13%, with an apparent age of 16,200. At 65 feet down, I got a modern percent about the same, and an age about the same, 16,000. As I came up 20 more feet, the age got a little bit younger, and the percent modern water, newer water, increased. As we go down towards the portal, we see that the percent modern water and the water age increases. So at the no name, we're up to almost 20% modern, but we're still looking at about 13,000 years as the mean age. As we come out closer to the portal, the Bachelor Shaft is looking to be about 28% with an age of 10,000. And the portal itself goes to about 33% modern with an age of about 8,800. So pretty clear trend here. The age gets younger as you move from back to front. And the age is pretty darn old when you get in the back. And so this is suggesting that a lot of the water in the back of the mine is at least a big portion of it has to have spent a long time underground. So it probably is not showing up, certainly is not showing up from the snowmelt last winter. So kind of to bring it all back to wrap here and look at the big picture, back to this, I'm working on this diagram, it's not very pretty, but a hydrogeologic conceptual model. So what our conceptual model is, remember these dueling approaches of new water versus old water, our beginning conceptual model is that the recharge occurs in high elevations as infiltrations of snowmelt, which we're pretty, pretty commonly, we know that the majority of precipitation that occurs at the high elevations here, so as you're going up towards the Continental Divide, you get more snow than rain, major driver, and the groundwater entering the workings is old based on our tritium and our carbon-14 dating. So there's your question, the temperature of the water in the Nelson Tunnel, 18 to 20 degrees, so I was a little down, it's actually a little higher. And what causes that temperature is currently in debate. Obviously, there's some degree of geothermal temperature, but the understanding of whether or not we have deep geothermal waters circulating, or if it's just the geothermal heat penetrating through the geologic material and causing that. Or a third approach right now is whether or not chemical reactions can do enough in these areas of mineralization to increase temperature. So the flow paths, deep and slow, and that's relative to the geology. And let's see. What I want to point out is, so if we think about high elevation recharge, water coming down, there's a bunch of things that are complicated. One is the equity fault goes perpendicular to these other faults. So if you think about water coming down and hitting something perpendicular, that may drive it deeper into the ground, and it may move it. So one of the things that we're thinking about now is the water that comes out of this Nelson portal, if it's coming in and getting pushed over, and we believe that this water is coming from deeper in the ground up. And that is based on the fact that the mine workings are not wet. The Commodore 5 level is dry, pretty much dry as a bone. You don't see water dripping down from above, for example. Based on mining records, we know that when they went down below 9,000 feet, below the level of the Nelson, they started encountering more water, which suggests the water was coming up. Now the level of water is obviously at the Nelson because it comes to that area, rapid flow path to the surface. And so the question is this deep water, how connected is it to the Bulldog Fault? And this comes into play moving into the future, because this is potentially a future mining area where they'd like to go back in and start working potentially. And the question being is, what's the connection between water? So we're trying to get at that now. I do have a sample of water in here. I'm not allowed to test it for some things I am, and that's up to the mining company to decide. It's their right. But we're looking at that. We're looking at water from a domestic well on top here. Perfect, last slide. And we are trying to figure out the connectivity. One question is, if this mine were to reopen, they would most likely need to do dewatering. If they wanted to go into the elevations, these elevations of workings in here, are fairly similar. And if you were to do dewatering, what does that do to the other side? So we have some information that previously, when the Bulldog was active, that the water that was in, when they did some dewatering in activity there previously, that water at the Nelson Portal dried up. So they pumped down on one side and dried up on the other. So there's one indication that those two are connected. The question being now is, if they dewater, if they open a mine, what does that do to this? How does that change the whole scenario of treating this water? And then the other question is there any chance of, so we talked a lot about treating acid mine drainage, and there's different active and passive treatments of dealing with the water coming out. But the other approach, which I guess I would characterize this, is stopping the sources. So source control work. So the idea being, could you go in and get this water to not come into these mines? Could you drill into the ground, pump it out, and put it in West Willow Creek up here instead of down at the bottom? And would the water quality, the $1 million question is, if you put a $1 million well in and pull the water out, is it good water, or has it already been mineralized because it's in fractures and it's acid mine drainage anyway? So those are some things to think about. I'll leave you with a picture of my sunrise this morning on my way over from Boulder. This is in South Park. And thank you for your time, and I'll take any questions.